Shall I start?
Yes, please.
Yeah. So, welcome to the IPA Colloquium to be delivered by Professor S. Ananta Ramakrishna. He is a director, CSI Laboratory at Chandigarh. Today is a very special day for Department of Nanoscience and Advanced Materials, Saurashtra University. This is an opportunity for the students and faculties of my department at Rajkot in Gujarat to co-host along with the IPA, Dr. Professor Vandana Nanal from TIFR. When we had a talk about this colloquium, I readily agreed. And she said that this will be a great opportunity for the students also. And I'm very thankful to the IPA to give us opportunity to host this IPA colloquium. In Gujarat, Rajkot is a very big chapter of IPA from 1978-79, when our founder of the physics department, Professor R.G. Kulkarni, he was very active in the IPA activities. And again, we would like to reactivate various programs under the IPA in the Gujarat and Rajkot chapter. So with these few words, I pass on the mic to Dr. Vandana Nanal, and then I will introduce our today's speaker after she speaks about a minute. Vandana ji.
Thank you very much, Professor Kuberkar, and thank you for hosting this IPA monthly colloquium. So I'll just take this opportunity to introduce the IPA to the young audience. As Professor Kuberkar said that Rajkot has a close association with IPA for many decades. But for the students who may or may not be aware of IPA activities, I'll just take a couple of minutes to say about what does IPA aim to do. So the Indian Physics Association was founded in 1970 with a goal that it likes to advance and disseminate and the application of knowledge of physics. Basically, to bridge a gap, provide a platform to facilitate interactions between the researchers and the young researchers, aspirants who want to pursue the physics. And how does IPA achieve this? It does it through a regular publication of a bulletin, which is the quarterly magazine Physics News, various later reports, and sometimes even books. It arranges seminars and special programs, lectures for students, teachers, and young researchers. Some of the regular lecture series are the DAE CV Raman lecture series. We hold 5 lectures every year. There is an IPA also liaises with the international societies like American Physical Society, Institute of Physics UK, and APS, that is Association of Asia Pacific Physical Societies. Recently, we have signed an MOU with Italian Physical Society. So IPA has an exchange program with IOP UK. So alternate years, people from India, the scientists from India go to UK, and other year the scientists from UK come to India. These lectures are called Bhabha lectures in UK and are called Cockcroft-Walton lectures in India. We have a Professor P.A. Pandya Endowment lecture. IPA also sponsors or co-organizes conferences. Recently, to celebrate 50 years, we had a webinar series, New Horizons in Physics. It was supposedly actually an in-person workshop, but it became a webinar series given the pandemic situation, and that actually opened up new avenues, because it's like the challenges turn into opportunities because of the IPA then made its presence in the social media, and through that we have been able to reach out to the different to the wider community in the country and different corners of the India. We received a very enthusiastic response to this webinar series. All the lectures of it, there were 27 of them, are available on the YouTube, and you can visit the IPA webpage and get the links. You can subscribe to the IPA YouTube channel so that you will know about the future events, and of course the details are available on the webpage address which is given here. We invite you all to become the IPA member. It is very easy, so everything is available online, and if you have any issues, please write to the email address which is given on the web page. The idea, the enthusiastic response which we received for the webinar series New Horizons in Physics gave rise to this idea, and we hope to conduct this monthly colloquia on the first Saturday of every month, and this is the first of the series. I am very, very thankful to Professor Kuberkar and Anant Ramakrishna to agree to give this colloquia. Our focus for this first part of the colloquia is going to be actually looking at novel opportunities with physics research as well as the beyond in terms of looking that. And with this now, I hand over mic back to Dr. Professor Kubherkar. Thank you.
Thank you, Professor Vandana. So I take pride in introducing the speaker of the day. Today, we have with us Professor S. Ananta Ramakrishna, who received his master's degree in physics in an integrated 5 years program from IIT Kanpur in 1995 and received a PhD degree from the Raman Research Institute, Bengaluru in 2001. He worked on the theoretical aspects of light propagation in random media, including temporal signatures of Anderson localization during his PhD. And he was supervised by a very great physicist, late Professor N. Kumar. After working as a postdoctoral researcher with Sir John Penray at Imperial College London, he joined IIT Kanpur as an assistant professor in 2003, and he became a full professor in 2012. He joined CSIR-CSIO, that is the Central Scientific Instrumentation Organization of Council of Scientific and Industrial Research, Government of India, as a director in 2020 on leave from IIT Kanpur. The current research interests of Professor Ramakrishna include technological applications of metamaterials and plasmonics. His publications and citations are found on his Google profile page. Professor Ramakrishna has worked in the area of metamaterials and plasmonic nanostructure materials and has published several papers in the refereed international journals, over 75 papers in conferences. And he has contributed in the research monographs entitled Physics and Applications of Negative Refractive Index Materials. It's a very, you can just see, now I am telling the distinctions and honors at this young age. He has received the fellow of IET, Institution of Electronics and Telecommunication Engineers in 2020, and a very prestigious SS Bhatnagar Prize for Physical Sciences in 2016. He has received the Swarna Jayanti Fellowship of Physical Sciences in 2012, and he was a INSA Young Scientist Medal for Physics 2007. Such an important distinction and honors have been received by Professor Ramakrishnan. So today, he will be giving a colloquium on waves in structured materials, a world of new opportunities. So I request Professor Ramakrishna to deliver his colloquium talk. Thank you.
Yeah, thank you, Professor Kubherkar. I am really sorry for the delay that happened before I could join. My slides were not visible on my software, and I was really fighting it out, and it was just that the software hanged. So, apologies for nevertheless, and I hope I can now come back to you. So, while I will now share my slides.
Yes.
Let me go full screen. Yeah, are you able to see the slides?
Yeah.
Yes.
Okay. So, let me give you my first introduction to the Indian Physics Association. Maybe that will, the students will like that. I was a trainee in the Baba Atomic Research Center, BARC, and we had one professor who told us, one faculty member who told us, look, there is this Indian Physics Association, you all should be part of that. And some of us asked, why ever? He said, no, you will partake in all kinds of physics and so on. You will have a lot of opportunities. See, being at that age, opportunities, all of us picked up our ears. Okay, whatever the opportunities were worth, whatever they were, we weren't too bothered about it. But he then gave the punchline. You better become life members now, because after 3 more months, the life member fees is going to double from 500 rupees to 1,000 rupees. The whole class, that was the conversion. The whole class became life members. And that's how I ended up becoming a life member of the Indian Physics Association initially. But I think the Indian Physics Association is a wonderful organization. It is run by people who mean so well on actually carrying out a scientific, generating a scientific temperament inside the country everywhere through physics education, through, understanding physics in a holistic manner. And they have done a wonderful job of encouraging physicists through awards, through, nurturing students and even older physicists through the lectures that they organize and so on. And I thank you for all the opportunities that I have received from the IPA all these years. Thank you very much. It has been a wonderful journey. And I really feel elated today that I've been asked to give the IPA colloquium. So, Dr. Nanal asked, and Professor Arun Grover reminded me. I just said, yes, of course, I want to do it. So here I am. So what I'm going to talk to you today are about structured materials and wave phenomena. And this is an area that I have been working, let's say, in the past 20 or more years. And principally, I first thought I would make it very general, like, the earlier title indicated. But then I realized that it would actually it would become that we will be talking about today for electromagnetism would be very applicable to acoustics, sound, to waves in water. Let's say you can think of a tsunami as a equivalent of a femtosecond optical pulse. These are applicable to seismic waves as well. And that is giving rise to a new technology to control seismic waves, which I will indicate at an appropriate point. It applies to waves of all kinds, to new kinds of shock absorbers, to whether, you can make new kinds of tires for automobiles, which are noise free and so on. So the general ideas are, they kind of extend across wave phenomena. But I will be principally talking about electromagnetism as a primer, because then I can actually physically show you things that we have done in the laboratory concerning that, right? So many of these structured materials are called metamaterials. There are various kinds of structured materials. There are materials that are structured at very small scales, and those are metamaterials. And I would be mainly concentrating myself to that today. So meta implies metaphysics, like metaphysics, and metamaterials implies composite materials with structural units, which are very small, much smaller than the wavelength of the wave. Although we may say radiation in the context of electromagnetism, it is a wave in general. And what these structured materials do is, because of their structure, they provide properties that are not usually found in natural materials. And the metamaterial properties may have very little to do with the bulk material properties, which make up the structures, right? So there is an optimized multifunctionality that is typically expected in metamaterials, because if you're going to take the trouble to make a nice structure, you might as well ask for more. And that is something that we do. See, the point is, when you have these structures which are very small, which are discerned by radiation, then there is no scattering from them. So for students, I would say that you have light that comes in, scatters off various objects. That's why you see different things. Let's say you see a book in front of you, that's because light falls from somewhere, it scatters off the book. Now, the point is, what are the scattering objects? The scattering objects are small particles typically. And these small particles will scatter light in an isotropic manner if they're very small. That's what happens to light scattered by, let's say, molecules in the atmosphere. So in a similar manner, when we have metamaterial structures, we expect them to be small enough that it is mainly the dipole scattering that will dominate. And the metamaterial structures are not very far away from each other, so the light never sees them individually. They are all close together within a wavelength, so the light cannot discern them. There is something called a diffraction limit, whereby a wave cannot resolve something smaller than its own wavelength size. So what happens is, when they scatter off, you don't see individual scattering, but you just see a bulk, effect of slowing down a wave. For example, you take glass, You have individual dipoles inside glass, right? I mean, you have individual molecules inside glass, silicon dioxide or silicon oxide. Now, however, what happens is you don't see the light scattered from individual molecules. You only see that light goes through glass and then refracts. That is because that is a net effect of all the molecules working together. But whereas if you reduce the size of the wavelength and you use X-rays instead, you would actually start seeing the molecular bonds. If you take a crystalline quartz, you will see all the X-ray diffraction spots. Now you are able to resolve individuals because your wavelength has become smaller than the intermolecular distance. So this is the whole point. When you are having small objects which are close together, you will effectively see these small objects as a homogeneous medium. The wave doesn't see them as an inhomogeneous medium. It sees as homogeneous. But then the wave will feel the individual responses within the medium, the polarization, the magnetization that comes inside the medium. And these are what you actually, call them as effective medium parameters like dielectric permittivity, epsilon, or the magnetic permeability, mu of the material. And these can be enhanced if there are any resonant responses. What that would mean is the polarization in the medium or the magnetization in the medium is highly enhanced. So this leads to an exceptional simplicity. See, you had a very complicated medium. I'll show you pictures of those. So just hold on with me. If you have a very complicated geometric medium, of all kinds of geometric shapes and sizes, you can just simply even think of a bunch of spheres, pack it inside a plastic bag, a small, let's say, metallic steel balls, which you find in any ball bearing, pack it inside a plastic bag. And you say that if I put an electromagnetic wave, which has wavelength much larger than that, let's say a microwave from your mobile phone, then this would behave as an effective medium. Yes, it would behave as an effective medium. But then if you wanted to describe what is happening to the electromagnetic medium inside every nook and corner near the sphere, in between the spheres and so on, it would be a very, very complicated situation. Then what would you be able to design with those? Nothing, because the description itself is so complex, you get lost in it. But whereas if you say that I have some effective parameter, which I can deduce from all of this, then you can use those effective parameters to design things with that medium. Let's say you make a lens out of that medium. You make a quarter wave plate out of the medium. You make optical elements out of the medium. You make detector out of the medium. Whatever you want to make, you can start making out of that medium. This homogeneized effective medium description allows you a considerable simplicity. And that is what we are looking for. So metamaterials, of course, as I said, we want unusual properties. Some examples are very large, positive dielectric permittivity, magnetic permeability, and surprisingly, the refractive index can be negative. The dielectric permittivity and magnetic permeability of a medium can be negative. And this actually occupied the interests of physicists for about 10 years, intensely from between 2000 and 2010, when we debated all kinds of possible aspects about it. You could have very large anisotropy. So for students, let me tell you what is an anisotropy. Let's say if it means different directions are not equivalent. If a wave, let's say, propagates in one direction with polarization in one direction, let's say in electromagnetic waves, the polarization will be perpendicular to the direction of propagation. So let's say the polarization is along the y-axis and it propagates along z. Or if the polarization were along x-axis and it propagates along z, then what would happen is the polarizations would travel in a very different way if the medium did not have equivalences in the directions. Now what happens is many crystals is because of the anisotropy in the crystal, in the arrangements of the atoms or molecules in the crystal, you can generate an anisotropy. But that anisotropy is typically very small. So here, whereas in metamaterials, you can generate anisotropies which are extremely large, so large that we never knew of them, such things, before we came to optics. I'll explain some of those. You can do what is called perfect impedance matching for microwaves. You can generate chirality, and you can have very large field enhancements. And in fact, one of the limitations of this field has been materials to create selective absorption very, very efficiently. All right. So I will just request everybody, if they have any questions, you can ask me in between if you really feel bad, or or you can put up your hand, and then I can quickly take some questions if you are really not following. Okay. So I think Chirag Savadia has a question. So if you can quickly ask me, I'll move on then.
Chirag, you can unmute yourself and ask the question. So maybe we take it later.
Anyway, if you have questions, the alternative would be to keep writing them into the chat box. So at the end of the talk, we will keep talking to you. So the point is, there are some issues that have happened in my slides. As you're able to see, things are moved around. See, the thing is, you all know the Lorentz model, which you have studied in your college, all right? And what we really are talking about the Lorentz model is you have a bunch of oscillators which respond to an electromagnetic field. And the response of the medium gives rise to a polarizability, which is resonant. So there is a frequency dependence. And this frequency dependence comes because the molecules are very willing to oscillate at a particular frequency. And that depends on the structure of the molecule, the bond strength, typically. But the same idea can apply to larger objects than molecules also. So you can have a bunch of, let's say, dielectric spheres. The dielectric spheres have a polarizability. And the medium, because of the medium properties, they would have a particular frequency at which they have a resonance. So that would also create such a polarizable response of a medium composed of dielectric spheres. So finally, what happens is there is a form of the dielectric permittivity, which was proposed by H.A. Lorentz back in 1909 and 1908. And that is pretty much a workhorse expression, and it works very well across for various materials. Now I'll just go over to some materials and show you. So for example, what are the different kinds of metamaterials that you have in nature? You can consider the simplest one would be just an array of wires, thin metallic wires. So if you had thin metallic wires, what happens is you have doped vacuum with metal effectively. And so you have a very dilute distribution of electrons, because the electrons are present only where the wires are. And if the wire array was very dilute, very sparse as well as very thin wires, then what happens is you have very small electron density. But because of the connection of the wires, the electrons can actually travel. So the whole system looks like a plasma of free electrons. But then this plasma has one very peculiar property. The electrons have to travel inside the thin wires. So the thin wires have a very large inductance. And if you have a large inductance, what does inductance do? It prevents currents from changing magnitude or direction. And similarly, what does mass do? It prevents objects from changing their velocity, direction, or magnitude. So the same thing, inductance is an inertial effect. So similar to mass, it works very similar to mass. So what happens to these electrons which are actually sloshing up and down the wires? They tend to, it feels as if they have tremendous mass, which is actually caused by the induction. So if you look at the plasma frequency is given by an electron density divided by effective mass of the electron. Effective mass in these wires for the electrons feels very large, but the effective electron density in space averaged over so many wires seems to be so little. So you can have very low plasma frequencies Typically, metals have plasma frequencies in the ultraviolet frequencies. These kind of materials can have plasma frequencies at gigahertz. Similarly, you can generate materials with magnetic permeability, which is resonant. So for that, what you do is you can, for example, a very good example is you just take a stack of metallic cylinders, as I have shown here in this place. And let's say you have an electromagnetic wave which comes in with a magnetic field polarized along the cylinders. This fluctuating magnetic field will, kind of create currents, circulating currents in these cylinders that shields the interior of the cylinder. That is Lenz's law. So now what happens is, if you can actually give the cross section of these cylinders like this with capacitive gaps, here you had inductance, now you also have capacitance. Each cylinder actually works as a resonant circuit. And this resonant circuit means you have a resonance at which, a point at which this whole cylinder resonantly magnetizes. That actually creates a bunch of such cylinders would create a magnetically resonant medium. And you can have a very large, if you look at the magnetic permeability, you have a resonance, and about the resonance at certain wavelengths, you actually have negative magnetic permeability as well. So all these are possible things, and these are all been realized. Let me show you a few physical examples of such things. So look at this metamaterial where you have cylinders of such a rolled up sheet, which has capacitance in between the adjacent rolls. And this is the example of such a cylinder. And this was the world's first metamaterial actually, which works at RF radio frequencies, 25 gigahertz or so. And then you get such a resonant response for the permeability of such a medium, which was actually made by Marconi. Now to students, I will say that this is a metamaterial that you should really feel inspired about, because this metamaterial, what it did was, you had this metamaterial which was just rolled up by a student like you for a summer project. So he had a sheet of copper, he applied nail polish varnish inside, or paint varnish inside that insulated the sheet on one side, rolled it up, painstakingly rolled up each one of these to have identical magnetizabilities. And he would actually individually measure these and then made up such a large numbers that it became a metamaterial which could be used. And in fact, at Imperial College, they tried to do MRI scanning using such a material. So summer student efforts can actually lead to really, a lot of very fundamental work as well as a lot of technological advantage also. Now here is the more modern component of this, where people used 3D printing to build up lots of such small units together, but actually change the density of these or the designs of these units over space, so that they actually built a lens for microwaves. And this lens actually has very, very little absorption. It has very little aberration. It can work beautifully for even rudders. Now, these were the world's first microwave metamaterials. There were, these were composed of those rings that give the magnetic properties, those wires that give the dielectric properties. And, you had these these particular metamaterials. They were developed in about 2000, 2001 or so. And they actually gave rise to a lot of interest. Now, as you go to higher frequencies, typically what happens is you do not have the capability to make three-dimensional metamaterials. It's too expensive, because if you go into terahertz, you have to make things that are sub 100 micrometers. So you can no longer make it by hands. You can no longer make it by ordinary processes. You have to have very good, manufacturing processes like laser micromachining, or equivalent things like lithography and so on. But then what you do is, when you can make them, people, for example, experimented with various things. In this example, I'm showing you a metamaterial which was not made out of a metal, but by actually a high temperature superconductor. People were trying to understand in this case, how does the conductivity of the metal affect the resonance? Here you can see, for example, in the normal conducting state, if you just have the conducting metamaterial, this is the kind of resonance you get. But if you actually have a superconductor, you get the red curve. The resonance is extremely sharp compared to the other case. Or you could have advances in lithographic techniques and MEMS techniques, whereby you can start orienting these in 3 dimensions, and you can make a 3-dimensional metamaterial even at micrometer scale. This is also something very exciting for many of us in the field. Then you have all these even finer metamaterials. Here is an example. Look at this example. The sizes are minuscule, and they are so small. Here you can see that at about 100 nanometers, you have these ring-like structures, 3-dimensional structures made on a surface. All right. Now, this actually has negative magnetic permeability at infrared resonance frequencies. And that was something very special, because people could not get magnetic properties in any natural material at infrared or optical frequencies. And as you go up in frequency, the size of the wavelength goes down, the size of the structures falls further. So finally, you are left with at optical frequencies, you are left with sub-100 nanometer featured structures, only which work. And here I'm showing you an example of the Indian effort here. This one was made in 2010 or 11. This is India's first metamaterial at infrared scales, where it has a negative magnetic permeability at 1.3 micrometers here. And similarly, you can try to scale them up over different depths and so on. But typically, you really need a lot of nanofabrication techniques such as lithography or ion beam milling and nano imprint and so on. All these play a very great role. And this is what was happening till about 2012, 2013, and so on. And then onwards, people started looking at what are the real applications that you can make out of them. So I will deal with a couple of applications so that you understand what are the kind of things that are happening. Let's take the really old problem. How do you make a perfect absorber in physics? We all talk of perfect absorbers, right? I mean, right from school, we say that when we want to define a black body, you want a perfect absorber. So let's ask the question, can a wave be perfectly absorbed by merely increasing the absorptive property? And the answer is something that you can see by writing down the Fresnel's reflection coefficient from let's say, a flat surface of that medium. The Fresnel reflection coefficient is nr plus I times ni minus 1, and so on. This is something you learned in the first year of your physics program, BSc. And then you look at this and take the imaginary part of the refractive index you would have learned there, typically represents the absorption in the medium. So if absorption has to increase, you increase the imaginary part of the refractive index. But then if you look at this expression and take ni to infinity, you find the reflectivity goes to 1. I mean, it just doesn't absorb anymore. So what's really happening? What's happening is the wave is reflected out, so you can't absorb anymore. So how do you get it to absorb? What you need to do as an electrical engineer would say is, you don't need to match the index. What you need to match is the impedance. And this is something electrical engineers, if they're an electrical engineer, immediately have told us, saying that look at the impedance instead. And that means you have to manipulate both the magnetic permeability mu as well as the dielectric permittivity to make the ratio roughly 1. And till recently at optical and infrared frequencies, there was no possibility of doing that, because mu was 1 for most natural materials. But metamaterials give you that opportunity. And that is why it is very important what we are going to talk about. So the first perfect absorber was demonstrated in about 2008 by Landy, by Willy Padilla's group in Boston College. What they did was I'll just call your attention to this panel, that's all. What they said was, I make a metamaterial where there is a resonance structure on top, which I can polarize, and I can create a polarization. And behind this, a certain distance away, I put a metallic strip So that when let's say, if you look at this particular picture, the electric field vector is in the vertically upward direction. So if I put the electric field like this, these rings will get resonantly excited, all right? And then what would happen is the currents would go across the capacitively across this dielectric in between, and it would come down the metallic stripe on the back, like what is shown here. So that sets up, if you think about it, a circulating current between the front and the back of this system. And effectively, you create a magnetic resonance also. So you have to match the electric and magnetic resonance in the system by the geometric sizes. And when you do that, you do get resonant absorption, and this is what people measured. And this is something that was very surprising for electrical engineers too, because you see, what before that, what we used to do, if you wanted to make a microwave absorber, you would actually think that, let me place a resistive sheet at distance lambda by 4 away from a metallic surface, or I would actually make these very bulky pyramidal absorbers having carbon, which slowly absorb it out, and so on. So for electrical engineers, this was something great because you could actually do it in a very, very thin sheet. It could be just a PCB, printed circuit board, which was just a millimeter or two thick. And this actually gave rise to a huge interest because of that. And there were alternative microwave absorbers similar to what I had shown you before, which were made by a few people, but all of them were, uh, difficult to make. It was this planar, printed circuit board nature, which may quasi two-dimensional nature, which makes it very easy to make. In our group, we were simultaneously thinking of using the same thing for infrared absorbers, because we wanted to control absorptivity of infrared absorptivity of surfaces. And we extended a lot of these ideas into the infrared. And we said that what we effectively do is something very similar. You have an antenna here on top, which could be just a circular disc of gold. It's a scatterer or it's an antenna, either way you can think about it. And you put it in front of a conducting film at a certain distance. And then you actually end up with certain medium, and then you have a conducting film here. So what happens is light comes in, it excites the electric field excites a dipole. It is polarized in the horizontal sense. It excites a dipole across this disk. Now what happens is that electric dipole creates a current on the surface of the disk, which creates a image oppositely oriented current on the thin film out here above. So the conducting film actually gives a mirror image of the current. Together, these two circulating currents give rise to a magnetic field. So you have a simultaneous magnetic and dielectric resonance, and that gives rise to an absorption peak at infrared frequencies, which is, and because of the way we chose these polarizations, the symmetries of the disk, there was hardly any polarization dependence. We put it on a hexagonal or square lattice, which actually reduced any angle of incidence dependence and so on. So you had a pretty much broad band and broad angle absorbance, which was very high. Now you can actually make multiple such layers, and you can have multiple resonances, which is also something that we actually showed. And then, you could actually have such materials that we generated. So we actually made them out of various techniques by, using stencil mask machining, and we actually made many other things later on. All right. So the point is, you actually could generate these kind of infrared metamaterials, and you could actually get these kind of very nice absorbances, all right, which are very band specific. You could decide by the structure what is the frequencies at what is the wavelengths at which that light would be absorbed, and the absorption is typically 93 to 97%. And each of these bands here, these depend to specific multiple excitations of that circular disc or the antenna that you put on top of the metamaterial, what we showed. And we went on, did a lot of other things, like we started experiment on whether you can put them on curved surfaces. We made them on plastics. We developed various techniques for various applications and so on. And we actually moved on into using some indium tin oxide based metamaterials, because you actually have indium tin oxide, which is actually completely transparent to light, optical light, but it is actually very absorptive to infrared in this case. And there are certain applications that we wanted to push them to, particularly for military applications. We developed certain applications which are being tried out now. And it gives you dual band thing. You can actually coat a surface through which you can see things, and at the same time you have an infrared absorptivity control. So you can, here is an example where you have huge absorptivity here, but in this entire 8 to 12 band, you have a complete reflectance, and then you again have absorption. So these were actually developed for certain kinds of detectors where we wanted to kill the pink noise, where the 8 to we wanted no absorption in the 8 to 12 band, where we only wanted to sensitize certain other bands. So the point is, you can actually create various kinds of absorbances, various kinds of reflectances by using the structure. These don't depend on the material anymore, on the material properties, but they depend on the structural aspects only. So again, you can have active metamaterials. You can actually have a metamaterial with an embedded layer which changes its properties depending on its temperature. We, for example, used vanadium dioxide, which changes its property from a good insulator to a metal at about 68 degrees. If you go above 68 degrees, it becomes a metal. If you go below 68 degrees, it's a nice insulator. So various such things were actually done. And this is a patent for, for example, you can have a mirror that changes its reflectivity so sharply. In the hot case, it's highly reflecting. When it is actually cooler, it actually becomes highly absorbing at one particular wavelength band. And this is something that we have patented as a, complete Q-switch mirror for carbon dioxide lasers. And then we can have switchable. This is the way, for example, that I was talking about, the vanadium oxide that I was talking. These were made by my collaborator at IAC, Professor Umarji, and his student Bharati. So these films actually can switch very, very rapidly their resistivity. So, it goes from an insulator to conductor very quickly, over 3 orders or 4 orders of conductivity change over a few degrees. And these are actually used for infrared detectors. And these are certain metamaterials we made on them, and these are well known now. Here is an example. I will just show you very quickly. Here is a metamaterial where you can see that we can switch it from just a few percent all the way to 95% plus of reflectivity by just changing the temperature of the metamaterial. So metamaterials need not be something that are just static. They are dynamic. People have been switching metamaterials using femtosecond pulses. By with vanadium dioxide, it is not clear whether it is photo-induced or thermal-induced, but there are certain semiconductor-based materials with which you can switch very fast with femtosecond pulses or picosecond pulses. Even these switch very fast, but that's more of a thermal effect. Now, what happens is, when you have a thermal absorption, the thermal absorptivity and emissivity are equal. So when you choose a material, when you develop a material that has a spectral absorptivity, which is varying over wavelengths, that means you have also modulated the emissivity. This is called the Kirchhoff's law of thermal radiation. And what you can clearly see is, for example, if I take a metamaterial with this kind of a one structure, it has an absorption peak here. If I put 2 structures in a unit cell, then I have 2 absorption peaks. So this experiment, for example, shows that if you had a black body, that is the spectrum with which it would emit. Carbon black roughly does that at 300 degrees. But your metamaterials with a single peak, let's say like that, emits only at that frequency. And if you have two peaks, they emit only at those two frequencies. So they will emit always within the envelope provided by the black body. So what are you doing? You are actually allowing only those noise currents on the surface to actually talk to the atmosphere outside. And by that, you are allowing only those to emit, those bands to emit. So now you suddenly had a way of controlling the emittance of these kind of materials. So emittance control was actually thought almost somewhat impossible. And here is an example of what you can do. If you take our vanadium dioxide based metamaterial, what it does is it has high absorption and high emittance at low temperature and low emittance at high temperature. I mean, that's like you increase the temperature, it emits less. That's like countering black body radiation. Here is an example. At the LWIR, this is the metamaterial. This is actually a layer of silver paint to provide a reference, and the others are, you can just see that. So at low temperatures, it is actually emitting a huge amount, this metamaterial. It becomes larger as you approach the transition temperature, but you go above the transition temperature, it just cools down. I mean, it's not emitting anything. It's not like it's colder, it's actually hotter. A hotter object is emitting less infrared emissivity in this particular case. And that's simply because you have changed the emissivity. You switched the emissivity. The same thing can also be done in MWIR to a lesser extent in that sample, because the MWIR peak was smaller. The amount of extent of switching is much smaller there. So the idea was we could actually, make very robust metamaterials using materials called cermets, which we have actually pushed to, making, for very robust military applications. We are actually pushing that. I am hopeful that within the next couple of years or so, there will be a couple of military systems with those kind of those coatings. And there are certain other things that we could do. We could actually make a, perfect absorber using these kind of structures. And here is something that you can do. You can actually switch the nature of this by optical means itself. So what does it? I mean, you actually had a nonlinear absorbance in this system. So this was the absorption profile. And here I will show something that when you actually put in a picosecond laser incident on this system, as you kept increasing the average power, you actually started seeing here, if you look at the bottom, you actually started seeing lesser and lesser reflectances, or the normalized reflectance was actually reducing with increasing power. So it was becoming a better and better absorber. And that was actually quite surprising. And if you look at it, what happened was, initially our laser was somewhere here with respect to the absorption peak. And as you kept increasing the average power, the temperature, surface temperature started changing. And because of the thermal effects, because of the change of the dielectric permittivity of aluminum with which we had made this metamaterial, the conductivity went down and the entire peak shifted there. From the black curve, it went to the green curve at higher temperatures. So you actually started absorbing more and more. It's only a small amount of reflectance that was there, 4%, but you could actually reduce it to 1% by just changing the fluence that was there on it. And the same thing you can actually do something even better when you have a material that is not really optimized to give very small amount of reflectance. In this case, what we actually had to do was we used picosecond pulses. And when we used gold, these are actually made out of gold. The gold actually has a very small thermal conductance change, but it has a reasonable Kerr nonlinearity, and using that also we could actually switch the reflectivity. So for example, initially at low intensities, if the reflectivity was just about 25%, at high intensities, the reflectivity could be increased to, let's say, 25% or so here. So there were various reasons, and we found that it was actually a cubic nonlinearity and so on. So now with metamaterials, I have given you 2-3 examples where you can switch them, you can make them nonlinear, you can, this is what, in this particular case, as you keep increasing the intensity, the reflectivity gets capped at a particular level. So this is what is called an optical limiting. So we have actually demonstrated what is called an optical limiter here. And all the effects were due to nonlinear optical effects in these systems. And see, there are many other experiments that we had done with my collaborators at IIT Kanpur, where we were looking at microwave absorbers also. We had been looking for narrowband absorbers initially. Nowadays, we have such broadband effects that we can cover almost the entire electromagnetic spectrum, right from 4 gigahertz to 18 gigahertz and so on. So there are various kind of, here are some examples. These are some old examples that I'm showing you. But we can actually make them completely transparent. We have made transparent microwave absorbers, which are being used in certain defense applications and so on presently. Now I will switch gears and I will give you a very different picture of, move to a different effect. The different effect I would like to be talking about are what are called indefinite media. I'll just touch upon them for a few minutes before I close. And they're like, if you think about many of them, wire materials or whatever that I had presented here, when I initially talked about the wire medium, it's a plasma, sure enough, but if I have wires oriented along all 3 dimensions, I have a true plasma medium. It is isotropic. But if I had wires oriented in only one direction, like, you have these nanowires in a piece of nanoporous alumina, which also people have made, or if you can actually have aligned nanowires, which people are able to do that while growing silver nanowires inside a solution. If you apply an electric field, they actually straighten out. So if you had oriented nanowires, or if you had oriented wires only in one direction, which is what typically is possible in nanotechnologies, then what would happen? What happens is, in the direction along the wire, if you had polarization along the wire, electrons can go up and down. If you had perpendicular, then it is not a conducting medium. In one direction, it's a conductive medium. In the other direction, it's not. It's a non-conductive medium. So it's a highly anisotropic medium. So if you had highly anisotropic media, then I will just very quickly tell the students about this effect. What happens is, if you had media which are not equivalent in the 2 directions, right? The dispersion relation looks like this. See, normally epsilon z is epsilon x equal to epsilon x, and you would have the equation of a circle for a wave propagating in free space or in an isotropic medium. If they are now different, what happens is, this dispersion relation becomes the equation of an ellipse, and which is also known in optics, crystal optics. As I said, a small differences could be there. But with metamaterials, as you appreciate in this slide, the conductivity is very large in this direction. So it looks like a plasma. Plasma has a negative dielectric permittivity. In the perpendicular directions, there is no conductivity. So in that direction, the medium looks like a dielectric medium because the wires are not connected. It has an insulating medium in between. So when that happens, what happens is, one of them has a plasma-like character. Let's say you flip its sign to negative, and the other one is positive. So, or this can be negative, the other one can be positive. So from a elliptic equation, you end up with a hyperbolic equation. And these hyperbolic dispersions were completely unknown in optics or electromagnetics or anything that we had done before about 2004 or 5. We never knew anything about like that. Now, when that happens, what happens to the wave? The wave actually can do very, very strange things. Let's say you have light coming in from free space. This is the equifrequency surface. And if it is coming along perpendicular to the z-axis, on a plane, let's say this is the plane on which it is incident, then, the parallel wave vector is conserved. So actually you need to find a point on this particular curve for the given medium where the wave vector actually has the same horizontal component. And if you look at that, that would be the kind of thing that you would get. So this is the wave vector you would get, and that is the pointing vector that you would get. So you actually have refraction, which is opposite to the, on the same side of the normal, and all kinds of things you can actually start getting. So these are some very strange media. We call them hyperbolic media. And there are some very strange effects that we could actually realize when we could make hyperbolic media in the form of, fibers. You fill in radially emanating nanopores, and you fill them with wires. You actually create a dielectric tensor like that. And if you solve all of the Maxwell's equations, you start getting modes which start looking like that in the radial direction across a fiber. And the peculiarity is these are Bessel modes with imaginary orders, which are before this probably the only place they had been used was by S. Chandrasekhar in describing certain, uh, radiative transfer in some stellar atmospheres. You don't have much use for them in physics, and many mathematical research are also on these kind of Bessel functions with imaginary orders, quite recent. But what is the real property of these? What happens is you have this essential singularity in these functions at the origin, and they highly oscillate as you come towards that essential singularity. So in some sense, you must have dealt with, you must have been asked by your seniors, tell me how does sine 1 by x looks, or cosine 1 by x looks. Sure enough, as you come towards x going to 0, as you come near x equal to 0, this function will just keep on indefinitely oscillating without ever converging. So the same thing happens in this. And if you look at the profiles, in a normal fiber, which has positive index, as you keep increasing the angular momentum, if you keep increasing the angular number, then what happens is the wave modes will actually increasingly vacate the center of the fiber and move towards the periphery. But in these fibers, which are hyperbolic, the imaginary orders are the eigensolutions, and they will oscillate more and more as you go towards the essential singularity at the center. And what we typically do is to put a metal at the center or something to prevent the physical divergence, the mathematical divergence when you calculate that. But then you find that there is no such vacation of the center. It's actually quite clustered at the center. And these are certain acid, you actually form such pores which are nicely oriented in one direction and also quite periodic, hexagonal in an hexagonal order. Now what we do is we actually do that in the cylindrical geometry. We take a very thin aluminum micro wire and we electropolish it, reduce it to the thickness that we want, and then we anodize it, and we form these nice nanopores in the radial direction. And here are examples of such alumina nanofibers, and which we could actually fill with nice amounts of metal inside. And once they can be done by a nice electrodeposition. After all, you have an aluminum core, which can be used for a contact, and then you can fill in nicely some silver or nickel or anything inside these pores. And we could actually get some nice bent fibers which could carry light. We could get a separate output, and so on and so forth. So the point is, these actually can couple light to the far field very effectively because of there are certain ideas about how the evanescent waves work. But to keep a long story short, what I will quickly take you over is we also have these very nice nanorods that you can grow and oriented over a surface. And if they are conducting, again, you have other kind of anisotropic hyperbolic media, where in these cases, if you take these kind of materials where you have aligned nanorods of silver, you actually perpendicular to the nanorods, you have dielectric permittivity that is positive and dielectric permittivity that is negative parallel to the rod. I will keep the story a long story short and tell you that these have very unique properties, and we have actually succeeded in extracting more light from the near sources, a near field of sources, or like nano diamonds with NV centers that have been placed on these kind of nanorods and so on. So anisotropy is something again that can really be enhanced by such media. I won't get into those details. I will just stop here because I think I've already exhausted the time. and I will just ask for questions from students. The whole idea of this was to provide you with a introduction to the idea that if you have a lot of structure in definite manners, you can control wave phenomena in various ways. And today, whatever I spoke is not just about waves. You can control, it's not just about electromagnetic waves. You can, when I talked about electromagnetic waves, I've been talking them with a complete broad understanding that they could be microwaves, they could be terahertz, they could be infrared, they could be optical frequencies. And similarly, these ideas extend across to acoustic waves. There is a huge amount of work that has happened on structured acoustic materials. So people have been making acoustic absorbers. People have been making, in a similar manner, people have been making very small waveguides for acoustics. People have been, for example, with those acoustic absorber designs and cavities, you can design cavities. Now, one application where that is doing that is going to bring a great change in the future is, you look at the tires of automobiles. Automobiles have become very silent. Petrol engines are quite silent. And when a vehicle is moving at large speed, it is mainly the sound of the tires that you hear. And when you now talk of electric vehicles, which are almost completely silent, you only will hear the tires. So people want to reduce the tire noise. And how is that tire noise reduced? It is reduced. Where is the noise coming from? It is coming from the treads. It is coming from the fact that the entire tire acts as an acoustic cavity. So there are modes which it can actually amplify, the noise can be amplified, and so on. So people are now designing tires where all these things are taken into account, and these kind of structures are put into the tire to absorb those kind of noises. That's an example. There's a second example that I would like to give you. You take, for example, an earthquake. Earthquake is a seismic wave. It's a wave on the surface of the earth, on the earth's crust. Now, can you control that by such structures? And this was a research that was initiated by a good collaborator of mine, Professor Sébastien Guinou. He's at the Institut Fresnel in France. So they worked with a company which built the Lyon airport, and they made these huge civil structures. And they embedded them on the ground at various places. And they found that if you actually create waves on the surface of the earth, you can guide them around and you can push them to certain places. So I have not talked about one particular concept called the cloaking, where you can guide a wave around an obstacle. So it's like Harry Potter's cloak. You take light and, you guide it around Harry Potter inside the cloak, and you take the light out. Similarly, you build civil structures which can guide around a seismic wave around the structure you want to guard, and you push the wave beyond. So these kind of seismic engineering has also started taking place today. So, actually there is a company which has invested a lot of money in getting such a metamaterial seismic shield around one of their oil rigs in the North Sea, because it is in a seismic area. So it's on a seismic fault. So there are new ways of approaching all of wave phenomena, whether you are wanting to absorb a wave, whether you want to confine a wave, whether you want to guide a wave, whether you want to focus a wave. There are various things that happen, and all kinds of waves can be done, and it can be done by structuring materials. Then you are no longer dependent on the chemical and material properties of materials that are already available. So this goes beyond materials, and I hope that I have given you a glimpse of what all kinds of new things that have been happening in the world since about 2000, 2001, or so, when this field began. Thank you very much. Thank you very much, Professor Vandana.
Thank you, Dr. Kuberkar.
Yeah, thank you. Thank you, Professor Ramakrishna. Yeah. Yeah, thank you for a very illuminating talk. Actually, there was a question which was asked by me. I think he must have read
Let me just go to the chat box. Yeah. So
this is regarding the perfect impedance matching you told.
So how is that matched? Okay.
How this is accomplished actually, this perfect impedance matching, whether it's a self phenomena or whether the structure materials, whether how this achieved in structure materials.
All right. See, as I said that you have to induce two resonances, one which has a magnetic origin and then one which has an electric origin.
Okay.
So in the structure, you provide for both of them to happen and both of them to happen at the same frequency, because you control the structural sizes.
Yeah.
You can actually provide for both of them to happen in the same frequency.
Yeah.
And if that happens in the same frequency, what is going to happen, or very similar frequencies. So what happens is, around the resonance, the dielectric permittivity will disperse wildly. The magnetic permeability disperses wildly. So you have to match that dispersion, essentially. And then you get them to be approximately the same over a certain bandwidth. And in that bandwidth, you would have achieved perfect impedance matching.
Thank you. Yeah. It's
Or near perfect.
Interesting aspect, actually. Yeah, very interesting. Yeah.
So,
yeah, any questions?
Now, Ashish has been asking, which form of metamaterials is more suitable for absorber, nanopatterned or thin film structure?
Okay, yeah.
It would depend on the application. It would depend so much on the application. You can make them out of nanopatterned surfaces. You can make them out of thin film patterned surfaces, structured surfaces. If it is, for example, if you wanted to put it on the external of an aircraft, then you have to decide what is the correct thing you would want to do. You may not prefer the nanopatterned because it may be more fragile, but whereas the thin films could be quite strong. Or whereas if you wanted to put it on some other context, it's so context dependent. There is no single real rule. It will depend so much on the application and what kind of materials you can use, because all materials, you may not be able to create the nano patterns. There's a material compatibility question also that comes in. What material can you put on what surface? So it depends on all these kind of issues. So there is absolutely no common possibility.
Any other questions?
There are a couple of questions on YouTube, so maybe after we are finished with Zoom, we can come to the YouTube.
Yeah, come to the YouTube. Yeah, I think Zoom, there are no more questions, I think.
Okay. There are two questions here. So one is by Abhinav Chaudhary, says, how does different geometries of cavities affect wave propagation in metamaterials?
No, okay. Let me try to understand your question. You are asking, how do different kinds of cavities affect? So are the
cavity?
Are the cavities part of the metamaterial, or you're trying to put a cavity with a metamaterial?
So I don't know, but what he's saying is, how does a different geometry affect a wave propagation?
Okay, different geometries would have different modes. So now the frequencies or the mode structure would be different. The electromagnetic field or the wave field concentrations will be different, and the spatial distributions would be different. So the effective velocities, phase velocities would be different. So those are the questions that one has to ask. So different shaped cavities would have different wave properties. Yeah. And you have to adjust the metamaterials up according to the application one would need.
Yeah. Any more questions?
Yeah, there's another question which says by Dr. B.C. Chaudhary, what is meant by negative refractive index?
All right, this is a very enticing question for most physicists, isn't it? Yeah, because in school we always learn that velocity of light in a medium is c divided by the refractive index. And so what do you mean by a negative index? Does the wave go backwards? That's the whole question that one is asking, isn't it? Yeah. See, let me push it back to this. Let us go back. When you take any oscillator, and what happens when you excite the oscillator with the frequency just above the resonance frequency? What you will find is that the response of the oscillator is in opposite direction to the forcing field force. Any mechanical oscillator, you take a simple pendulum and force it. When you force it just above, at a frequency just above the resonance of the simple pendulum, you'll find that it will actually, the direction of the simple pendulum displacement will be opposite in direction to the force. So there is an anti-phased response. The phase actually jumps across the resonance. So this anti-phased response in terms of polarization, magnetization, if you think about it, will end up resulting in negative permittivity and negative permeability. Okay. Now, when both of these negative permittivity and permeability become negative, the refractive index, which you usually define through the Newton's relation as square root epsilon mu, the refractive index becomes a real quantity. If you had both one of the two as a negative quantity, the refractive index would be an imaginary quantity, which means the wave doesn't propagate into the medium. It just exponentially attenuates into the medium like in a plasma. Now, when both of them are negative, now what happens is the wave can actually propagate inside the medium. And if the wave is going to propagate inside the medium, then how does it propagate? Then you actually have to examine what is the nature of the propagation. You will find that the Maxwell's relations, which you write as K cross E goes as B minus epsilon, K cross E goes as mu B, and K cross B goes as minus epsilon E. When these two parameters have switched sign, those two equations switch signs. So the EKEB, the wave vector, the electric field and the magnetic field, which in an ordinary medium forms a right-handed triad, like XYZ, they will switch their order. Now what happens is KEB now form a left-handed triad. So the cross products actually look like that. But then the Poynting vector E cross B is still the same, right? That will not change. So a source remains a source. Light flows out of a source, even in those media. Sink remains a sink. What absorbs, continues to absorb. So the wave is flowing out of the source, but then the wave vector points towards the source in these media. So that is why we call them negative refractive index. So this is what is the phase velocity is negative, but the Poynting vector or the group velocity continues to be positive in most of these media. That is the difference.
Thank you. I have one general question. It was, of course, very, very nice talk, and you covered a lot of material and gave really a flavor of this completely new subject. And you did cover part of it, part of my answer. But I think since it is a lot of students are listening, maybe you could highlight, what is the kind of an opportunities for the future work in this area.
Let me do that. Let me go back to the slides, I guess.
Yeah, I know you did partly, but I just thought at the end you
could... see, I got stuck in this thing that, whether I should talk more applications or I talk more of the understanding. So let me just get to you. Give me to, just open that.
Sure.
Yeah. I will give an example of what is possible in these slides. All right. Now at IIT Kanpur, we had developed these technologies. Let me just share these things again. Are you able to see?
Yes.
Yeah. So for example, we had developed these kind of metamaterials for stealth purposes. So, when you have an aircraft or something like that, you just detect it using radars. And how do you detect it? Because of what it scatters, the amount of electromagnetic waves it scatters. So nowadays you have these stealth aircraft, right, which actually have these kind of absorbing materials on the surface of these aircrafts, and they actually they actually reflect nothing. So in recent times, a lot of metamaterial based absorbers are in use for across the world, not just yeah. So for example, we have been developing these kind of very, very broadband absorptive metamaterials, which can absorb practically over the entire radar band. And this is a joint effort in my team, which has been going on with 3 of us professors over the last 8 years or so. We have, for example, developed these kind of optical metamaterials, which you would hope to put on, let's say, the canopies of aircraft as a very exciting application, or there are many other applications for those. All right, so there are optically transparent ones. Now, for example, in this optically transparent one, we have an absorption band that stretches from about 4 gigahertz to 18 gigahertz, which is what is needed for, military purposes. I'm just trying to excite the students here. All right. Now, you can actually have infrared surveillance systems, battlefield radars, and so on. So you may want to have clothes which don't which absorb the radar and change the infrared emissivity, right? You become invisible to them, like Harry Potter. Now, and these are things also that have been going on. So for example, you have clothes like these, which you put on tanks and so on, but they are invisible for, these, and we have developed such cloth materials also. All right. And you want to have infrared camouflage for thermal. Yeah. So many of those thermal systems that I showed you, thermal emissivity systems, you can actually put on a tank and you can change its surface emissivity. And these are certain military systems that I've been talking about. Here is, well, I would actually take quite a bit of pride on this metamaterial. This is something we can print even on sandpaper, as you can see in the middle. It's a microstructured metamaterial whose LWIR, long wave infrared emissivity, is almost close to 0. So it just looks black in the infrared image. So we can actually start hiding hot objects like tank engines or vehicular engines and so on and so forth. So there are various possibilities, and we have been starting to look at whether you can actually confuse a Doppler radar by creating, making active circuits, on top of these metamaterials which you put on aircraft and so on and so forth. So there are many, many such applications, at least in the defense domain. I showed you a few. Now let me go back and show you a few more interesting things. Let me go back to some old slides of mine, I guess.
There is one more question here.
Yeah.
Can we take that, or you want to show something more?
I'll just show you one more quick thing, and then you can see.
Yeah. I mean, this is really a very interesting thing how this metamaterials.
For example, here are microbolometric infrared cameras, which have these metamaterials on the detector elements. So you can actually sensitize these cameras to specific bands in the infrared, which was never possible till now. All right. And these are actually commercially available through FLIR now. It's a thing called CDIP infrared cameras, and these are actually available now. So people have started developing polarization sensitive uncooled detectors for infrared. All right, and this is all in 2014-15. People have been publishing them. Now, all these are based on metamaterials and plasmonic materials, typically metamaterials in the infrared. Here is, for example, something that people developed for terahertz imaging. So, when terahertz falls, you have a long cantilever and you make an absorber, a very efficient absorber for terahertz. And when you have this very efficient absorber, you actually, that cantilever actually twists. And using the reflectivity, you can actually measure the terahertz, and each one of them is an element. So if you have an array of elements, you actually do terahertz imaging. Here are certain quantum cascade devices on which people built metamaterials to make much more efficient detectors, because you see in these quantum cascade detectors, there are selection rules which say that the light which is incident normal to the detector will not be absorbed. So then, you want to look at light that is coming from very oblique directions. It is not really possible. So what you do is with these structures, you actually change the polarization of light and couple it very efficiently to the quantum cascade quantum cascade devices. So really speaking, the number of applications are pretty much limited only by what is our imagination, because what it really affords you today is that you have structure. You can play with the structure to generate the property you want. So you have to decide what you want, and that's it. Yeah, we can go to the next question. Sure, thank you.
So the last question is from Darshan Kanani. Sometimes stealth refers to paint. Is it also possible?
Sometimes it is. Can you please come again? Sometimes it is.
Stealth, STALTH, stealth refers to paint.
Still.
I don't know what exactly means.
Stealth refers to paint. There are paints which actually absorb, but it has always been a question whether you want frequency selective surfaces or paints.
Okay. Yeah.
I mean, both of their, paints which are absorbing, you have to have a thick enough layer. It actually peels off, it actually falls off, cracks off, and so on. And there are issues about it.
Yes. Yeah.
Okay, that's all from here. Over to Dr. Kuberkar.
Yeah. Thank you, Professor Vandana. Actually, very interesting aspects of the structure materials and their applications in various fields. Now we can see the variety of fields which today he has Professor has shown, and these are the really. Actually, I am very sure by listening to this expert talk by Professor Ramakrishnan, the physics community and mostly the youngsters now who are taking interest in these materials, new materials developments. So these metamaterials, an understanding of metamaterials is very, very important for the application point of view. And this talk will be highly beneficial for this young community and all the physics community. So I thank Professor Ramakrishnan for a very illuminating talk today, which he has delivered. Thank you very much. Thank you. Thank you. So I also thank the IPA and Professor Vandana Nanal to give us opportunity to host this IPA Colloquium, first IPA Colloquium, which will be continued on first Saturday of every month, and which has been announced by Professor Nanal, that this is a very interesting, and I hope in future also the IPA Rajkot chapter and our department students will very actively take part in all the seminars which will be coming in future also. It will plan. Thank you very much. Thank you.
Thank you, Professor Kuberkar, and we thank your department.